of a constant function? 0. Yeah? So this thing is minimized by constants. Now constants are boring solutions to optimization problems. So how do we keep away from the set of constants? Well, we say we're going to minimize E of f, right, over all f, but we're going to add a constraint, right, such that f restricted to the boundary is given. Right? Do you see how this is exactly the problem that I kind of laid out to you here? Right? Somebody observes a bunch of values around the boundary of a domain, and now I want to figure out an f that's in the interior. And how am I going to do that? I'm going to choose that f that minimizes this thing called the total derivative, which is measuring smoothness. Yeah? Because I want this thing to be really smooth. And the neat thing that happens is that this optimization problem, and this should be a scary problem to you guys. You see, I am optimizing over a set of functions. This is an uncountably infinite set of things. But the minimum here is guaranteed to satisfy PDE, and that's going to be how we solve it. So let's do that. It's very short, and I kind of like it. So, how are we going to do it? Well, okay, so let's say that in particular we're going to call the function on the boundary, we'll call him g of x. Just for notation's sake. Yeah? Okay. So now, let's say that I take So let's say that suppose that f minimizes E of f. Yeah? And now, we're going to take some function h on omega. Right? This is just some assignment of numbers to points in omega. Now my proof today is going to be wildly unrigorous when it comes to things that are differentiable versus things that are not. If you are interested in that, you should take math. I think it's 215 or something. It's very yucky theory. All about Sobolev spaces. That's what you should Google. Anyway, but that aside, for now we'll assume that h is infinitely differentiable, and it turns out that's okay. So what do we know about E of f plus h relative to E of f? Well, we know, I'll tell you that. We know that f minimizes E. Yeah? So if I change f, I perturb it by any function h, I gotta get a bigger value. Yeah? Okay. In fact, now I'm going to take some constant epsilon, I'm going to put him in front of this h. Right? And obviously for any epsilon this is true. Even when epsilon is negative. Yeah? So one thing I could do would be say, okay, let's divide this by epsilon. Right? Then, okay, so this inequality no longer makes any sense, but I can look at this quantity, yeah? And what happens when I take the limit as epsilon goes to 0 of this quantity here? Well, think about it. No matter what direction, no matter whether epsilon is positive or negative, anything, this thing has got to be bigger at any f plus epsilon h. Right? So particularly, that tells you this thing has got to be 0. Do you see why that is? One way to think about it is that really all I'm doing is minimizing some function, right? And well, what do we know? The derivative at the minimum is 0. And that's actually exactly the relationship I just did here. I'm going to take my f, right? I'm going to perturb him in the h direction, right? Which is kind of like moving in this direction, say. Right? And we know that when it's minimized, then this derivative vanishes. Yeah. This, by the way, was also on your homework. Yeah. This is should be familiar story. So this thing is called the weak or Gateau derivative of f in the h of E at f in the h direction. Right? You can see this is kind of weird what I'm doing, right? I'm differentiating a thing that takes in functions with respect to other functions. But even if that sort of high-level, scary, theoretical mess is difficult for you to keep in your head, the idea is nothing more than if I take a minimum and I perturb it at all, E has to get bigger. Yeah? That's all this is saying. Okay. So another way to write this object here, which is kind of slick, is, well, think about what I'm doing, right? I'm taking, oh, I'm sorry, I did this slightly wrong. You guys never catch it. There we go. This thing's equal. Right? because this thing is missing a sign. Okay. So this is obviously kind of yucky notation, so let's clean him up a little bit. You can say that this is the derivative with respect to epsilon of E of f plus epsilon h evaluated at epsilon equals 0. Cool. So you got, again, this looks complicated, but it's not. All it's saying is that I can take f, which we know minimizes this energy function. I haven't told you a way to find f yet, but if we did, and then if I perturb him by anything, I'm going to get a bigger number, and in particular that implies that if I move a little, this epsilon amount in any direction, it's going to get bigger, and that's going to give me 0 when I take this derivative. Cool. So now our job became far more concrete than when we started, right? Now I just have to figure out what this derivative is. Yeah? So let's call this thing, actually, we'll just do that. Okay. Well, so let's do a little bit of math, and what we're going to do is what's going to come out is going to be a partial differential equation. And then we'll say that this is the weak form of the PDE, and this is the strong form. Right, so to do that, we're going to say, okay, what is E of f plus epsilon h? Well, we have our definition here, right? So we just plug it in, and that's what we're going to get. So we're going to get, this is still the integral over omega, now the norm of grad f plus an epsilon is just a number, so he can come out of the gradient grad. Yeah? Okay, so now that we have this thing, in fact, let's expand him a little bit more. So this is good review from like the first 2 weeks of this class, right? A norm squared is equal to this thing dot product with itself, because these are nothing more than vectors inside of this integral. Yeah? So if we do that out, that's going to be the norm of grad f squared plus 2 times grad f dot grad h plus, with an epsilon there, plus epsilon squared norm of grad h squared. You guys should catch me if I do something wrong, but I probably will. Predictably not. Alright. So now, let's take the derivative of this guy with respect to epsilon. Yeah? Well, the derivative has nothing to do with the integral. The integral is over omega, but epsilon is just some perturbation of these functions. Right? In fact, you can move the derivative into the inside, and what you get is that this thing is the same as 2 times grad f dot grad h plus 2 epsilon grad h. Yeah? Hopefully I've done that. Yes, F. Okay? And finally, for my last trick, remember that we want to evaluate this thing at epsilon equals 0. And that gives us 0. So plugging that in here, we get this equation. 0 equals the integral over omega of 2 grad f dot grad h. Right? And this term just goes away. Right? Because there's an epsilon there. He's 0. Okay. This is super simple. This is a really easy relationship to deal with. Right? And remember, this is for any h. All I said was, take an h. And this relationship has to hold. Yeah? This is this very generic condition, but somehow h is hidden underneath this gradient, which is a little bit annoying. Now, if you remember on your homework, this tripped some people up, but in the end it wasn't so bad. You integrated by parts to get rid of this gradient on the perturbation, and we can do the same thing here. Integration by parts is also called, what, Stokes' theorem, I guess, and on higher dimensional things. But basically, it's just the integral of h around the boundary, and then you move the derivative to the other guy. Yeah, and this is, if you don't know this fact, this isn't something you're responsible for in this class. But if you took Math 52, then you did calculations like this just over and over and over again. Right? So we're going to add one more condition. We're going to say, take h to be any function on omega, and assume that h on the boundary of omega equals 0. I can do that, because I'm just going to take any h that I want. So I'm going to say in particular, take an h that's 0 on the boundary. Right? Remember how integration by parts works? Right? On this homework problem you just did, you got a boundary term, right? So you have it into 2 endpoints, and then minus the integral where you swap the derivatives. Yeah? So here, the boundary term vanishes because I just made it vanish. Yeah? And what's left is we're going to pop the derivative of the h and put it onto f. In particular, this thing is minus 2 times the integral over omega of h times the Laplacian of f. So even if you didn't take a multivariable calculus class, you might kind of divine this trick here, because basically all it's doing, just like integration by parts, is moving derivatives over. And since we have this slick notation where we think of this guy as an operator, we just move the derivative next to f and we get derivative squared. In fact, this turns out to be true. Now here's the thing. This relationship holds for every single h. You give me an h, I can guarantee you that when I take this integral, I will get 0 against the f that minimizes this e. Every single h. Yeah, it has to be 0 on the boundary, but that's not a big deal because the boundary is a very small set. Yeah? So I take any h, right? Maybe h is like some function that looks like that inside, and multiply h by the Laplacian of f, and integrate this over omega, I get 0. But you didn't say anything about h. So in particular, what this implies, I go through this in the course in a little more detail, is that, well, this thing had better be 0. Right? Because no matter what I integrate it against, I get 0. Yeah? So I just showed you that the Laplacian of f equals 0, and this is a partial differential equation. Right? So how do I solve for f minimizing e? Well, what did I prove to you? I just proved to you that if f minimizes e, then the Laplacian of f equals 0. Right? And so in fact, what we do is we search for functions whose Laplacian equals 0. Now, in case this story seems completely unfamiliar and new to you, which it might, I mean, this fun trivia fact of the day, AP Calculus actually used to have people take these sort of weak derivatives, but doesn't anymore. Anyway, even if it sounds unfamiliar, it really shouldn't. Because what did I do? I took an energy that looked like least squares, I differentiated it, and I got a linear-looking system of equations that I should solve. Exactly the same as our old story from least squares. Yeah? And in fact, if you really want to get funny about it, right, if you think of this thing as a matrix, a symmetric matrix, then this is nothing more than the normal equations, A transpose A. So you got a square there. Yeah? Now obviously, this is a very high-level sort of intuition here, but in fact it carries out, and that is precisely the reason why this trick works. Yeah? So a very common, so to make a short story very long, basically what I want to show you with this little derivation we did here is that a very common source for partial differential equations is actually exactly the same as the problems that we've been solving all quarter. Yeah? Where you write down some energy, now instead of taking a point, this thing takes in a function, but it's still some energy kind of measuring stuff that we want to be true. Right? In this case, that the function be kind of smooth. Right? And then we differentiate the energy. Now we need to do something a little more complicated, but the pattern is the same. And what comes out is a system of equations. Yeah? It's exactly the same. Remember when we did conjugate gradients? Right? We started with an energy. Now it's an energy of a point. Right? Remember that was x transpose A. X is a good final example. Minus B transpose X. And we really need a constant term. And I differentiated it. And I got A, X equals B. Yeah? Same thing happened. Just now it's a derivative instead of a matrix. Kind of cool, huh? So anyway, this is a lot of times I see PDE classes that sort of skip to the last step and write down like, well, suppose we wish to solve Laplace's equation, then we do the following discretization. I don't think that's entirely fair. But the reason why that we would solve an equation like Laplace's equation is that all it's really doing is just trying to find some smooth f that interpolates. And we know all about interpolation in CS205A. Yeah? So anyway, when you see Laplace's equation, you should immediately, your brain should think interpolation and smooth. That's what should happen. Yeah. By the way, interesting question, totally an aside, but just for the advanced math students. F needs to be 2 times differentiable for this equation to make sense. Yeah? I mean, the Laplacian's got 2 derivatives. But, well, what if I said a solution to the Laplace equation is anything such that when I integrate it against any function, I get 0 in this formula, right? This formula only requires 1 derivative of f. Yeah? So in fact, the advanced theory of PDE, all it does is basically pop derivatives off of f and put them on h, and then you get something called a weak solution of a PDE, where f might not be differentiable at all, but it still satisfies Laplace's equation. Anyway, it's a total aside, not important for this class, but kind of interesting. Right? Because in fact, the same trick I used to put grad squared f, well, I could have put grad squared h, right? And said, well, f is any function such that when I take an infinitely differentiable thing and I multiply them and integrate, I get 0, right? That requires no derivatives of f. Kind of an interesting thing to think about. Alright. So anyway, even if all of this lost you, the big high-level story here is I started with an energy function just like what we're used to, and I got a PDE out when I differentiated it. Huh? Totally reasonable. Okay. I promise we're not going to do any more hairy PDE proofs in this class. Obviously, this class is not about PDE, it's about discrete stuff. But I do think, since we don't know anything about PDE, it's important to do this one. Okay. So all the PDEs that I've written down for you, I guess minus Navier-Stokes so far, have been kind of linear looking, right? That you sort of have derivative times function equals some other thing, 0, or some other function, right? But sometimes you don't get so lucky. So an equation that's very important in what I do is something called the eikonal equation. Eikonal, by the way, is a Greek word for something, I forget. I don't know, somebody with a laptop can look it up. But yeah, the eikonal equation solves for distance functions. And this initially seems like a stupid problem, but it turns out to be a very challenging one and an important one in many applications in computer graphics and robotics. So the idea here, this should be a story that's familiar to Gavin again, since he took my class, is let's say that I have a domain omega, just like before, and let's say that I give you a point x0 inside of omega. Then I might write down a function on the entire domain here, which is the distance from x0 to that point. Yeah? So let's say this is x. Well, we know the shortest distance between 2 points is a line. Yeah? So you might say, okay, well, Justin, that's a stupid question. We can say our function d of x is nothing more than, well, the norm of x minus x0, not squared. Yeah? It's a distance function. And I would say you're 100% right, but what happens if omega is shaped like a jelly bean? And I want the distance from here to here, but I add a twist to this problem, which is that I say your distance cannot leave the interior of the jelly bean. Right? In other words, the shortest path between A and B now kind of goes like this. If you've taken CS161, this is the PDE equivalent of Dijkstra's algorithm. Right? I have some domain. Here it's like a blob, but in Dijkstra class, in Dijkstra it's a graph. I give you 2 points, and your job is to find me the shortest path. Yeah? Well, if I make you stay inside of omega, this distance is no longer a straight line, because you're not allowed to move in this little piece here. Right? So an interesting PDE question is, can I come up with a relationship between the derivatives of a function d locally that can help me figure out what this function is globally? And the answer actually is yes, and that's the eikonal equation. Now, one reasonable thing you could do would be to say, okay, well, what is the derivative of d? Yeah? So in fact, let's do that for this simple function d. Now, what is the gradient of this guy? Well, this is a little annoying because it's a 2 norm and it's not squared. Yeah? But one way around that is to say, well, this is the same as the norm of, or rather the gradient of the square root of d squared. And do anything. In fact, the distance is a positive number, so I didn't make any mistakes. Yeah? Well, okay. So now we can chain rule our way out of this, right? Because this, okay, so let's write the square root in a slightly different way. This is d squared x to the 1/2. Yeah? Okay. So what's the derivative of something to the 1/2? Well, it's 1/2 that to the minus 1/2 times the derivative on the inside. Yeah, there's a lot of words over that first. Yeah. Cool. So in other words, we have that this is equal to, well, what's this? The minus 1/2 is just 1 over the norm, right? So you're going to get this is x minus x0, 2 times the gradient of d squared of x. Isn't that tricky? What is the gradient of d squared? Well, that you computed 1,000 times on your homework. That's nothing more than 2 times this difference. So in the end, you get x minus x0 divided by the norm of x minus x0. Yeah? And this thing is the gradient of this distance function. Now, what do you notice? This thing is a unit vector. Yeah? By the way, what happens at x0? You're dividing by 0. And that makes sense, because your distance function looks like a v centered at x0. Yeah? But ignoring that point for now, this thing is a unit vector, and that's because basically all this is saying is that your distance changes at 1 inch per inch. That's all, right? It's you expect the gradient of your distance function to behave very simply, right? Because you're just moving away in a nice linear fashion. Right? So the eikonal equation says, in fact, any function which measures distance has to satisfy that property. That the norm of this distance function, not squared, is equal to 1. And this is a PDE, right? Because it involves derivative, right? The gradient is derivative in x and the derivative in y. Yeah? So written in another way, the eikonal equation is, you could say, the square root of d differentiated x plus d differentiated y, each of those squared, is equal to 1. Yeah? This is a horrible PDE to try and solve. Right? Because you are taking derivatives and squaring them. And so all of our fancy linear techniques fail. But it's an equation that we wish to solve a lot, and in fact, there are very good stable numerical methods for solving. You can see here that this gentleman has taken this unicorn, the whip, I don't know what it is, and computed distances from this red point here and, by solving the eikonal equation. And you can see that even though the tail is pretty close to the whip around the outside, because we were constrained to move along the interior, the distance is actually quite large. Methods for solving the eikonal equation, which we will not cover in 205A, are, most of them are called fast marching algorithms. And the really neat things that happens is that, in fact, the PDE solvers for the eikonal equation end up looking a lot like Dijkstra's algorithm, which is for shortest paths on graphs. Okay, finally, for our final example of a PDE, I suppose a better example would be a piano or a violin or a cello or something, but I happen to have Homer on my laptop, so I used him. One question would be, if I took a shape, like a violin or a cello or a Homer Simpson, and I hit it with a hammer, I'd like to figure out what the resonant frequencies are of that shape. It's very common in a field which, unsurprisingly, is called harmonic analysis. Right? This is important. When I design a piano, I want to be able to hit the keys on the piano and have nice overtones that are all about how the strings are resonating with one another. Well, it turns out that this is actually, to solve this, given the shape of an object or a domain, is nothing more than solving an eigenvalue problem, now for a derivative operator. Now this looks a little yucky, but it's actually not so bad. So for example, on a line, right, what is the second derivative of cosine? Well, the first derivative of cosine is minus sine, and the second derivative then is minus cosine, right? So you can say, well, cosine is an eigenfunction of the second derivative operator with eigenvalue -1. Yeah? In fact, cosine of kx for any k is an eigenfunction of the second derivative, the same argument. Yeah? Well, in fact, cosines are all sort of the resonant frequencies of a line, right? They're the nice oscillatory objects, and you can do the same thing for any shape by writing down the second derivative operator, remember that's the Laplacian, and finding its eigenstuff. And so what comes out are things like eigenhomers. And this is very useful in fields where you're trying to analyze a shape and figure out what parts of the shape are important, which parts will resonate, or for example, if I'm building a piece of architecture and I want to know what parts of my building are likely to fall in an earthquake, I might do very similar analysis to this. Yeah? Okay. So in general, PDEs require two things. For one thing, they require a relationship between the derivative, and they also require boundary conditions. Just like we had initial value problems, right? They told you what happened at time 0, and then we move forward from there. Here, I need to give you boundary conditions. For example, remember for the Dirichlet problem I wrote down, right? I gave you the values of the function around the boundary, and then I wanted to interpolate it in the inside. Right? So in general, these fall into 3 classes. There are Dirichlet conditions, which give you the value of the function on the boundary. There are Neumann conditions, which give you the derivative of the function on the boundary. And there are mixed or Robin conditions, which give you some relationship between the value and the derivative. Yeah? So for example, if I'm measuring heat flux, I might either attach the outside of a domain to a refrigerator, in which case I fix the heat at the boundary, or I might attach it to an insulator, which would tell me how the heat kind of diffuses out of the boundary. Or I would do some combination. Honestly, I don't know why you do that with heat, but sorry. Oh, so just like we had model equations for ODEs, remember y prime equals AY, we can have a model equation for PDEs, and it turns out you need a second derivative in there, because the first order PDE is not a very interesting thing to solve. Okay. So here's our model second order linear partial differential equation. Is that enough words for you? And basically all it does, you can see, is it sums up over all possible second derivatives of f, and first derivatives and, well, zeroth derivatives. Now I suppose I could have also included a term summing f stuff here, but nah, doesn't matter. Yeah, and a PDE would be one that satisfies all of this. Now, if we continue in this really slick notation that I've given you, in fact, this PDE takes a really nice form. Yeah? So I could take all of these aij's and put them in a matrix A, put all the bi's into a vector B, and so on. Oops, I suppose that should have been CF on the top. Apologize. Then, if you look, this, for example, this first term here is nothing more than that gradient operator transpose times A times gradient. Yeah? You can kind of see that, right? Because you have two derivatives with I and j, and they're picking up that entries away. Yeah? And so this is the thing we want to solve. Looks easy enough, but unfortunately is the topic of years and years of analysis. So we should step back and say, what do we want to try? Well, we really want to find something called a well-posed equation, which means the solution exists, is unique, and has some nice dependence on your boundary conditions. And not all PDEs satisfy any of these three. So in general, the way that we classify a second-order PDE is actually by looking at that matrix A. And it turns out that the proper way to classify is by exactly the things that we already know how to do in CS205A. You look, so if A is positive or negative definite, yeah, we know these words. If it's positive or negative definite, then you call the PDE elliptic. If it's positive semi-definite, we call it parabolic. And otherwise, we call it hyperbolic. In fact, usually what we say is if there's exactly one negative eigenvalue, we'll call that hyperbolic. And if there's a lot, this doesn't happen very often, but we call that ultra-hyperbolic. And there's very poor theory for understanding ultra-hyperbolic equations. And just like this, remember that like when we talked about conjugate gradients, because a matrix was positive definite, everything math just became easier. It turns out that elliptic PDEs are exactly the ones we know how to solve. Yeah? This is really cool. And the reason for that, unsurprisingly, is that elliptic PDEs come from minimizing a quadratic energy, just like what we did here. Yeah, so the stories actually move in lockstep between PDE and just solving linear equations like we already have. So let's go through these three cases, and obviously in 2 lectures I can't rigorously prove any of these facts to you, but I can at least summarize some intuition for what these sorts of PDEs are doing. Now an elliptic PDE, again, is one for which that matrix of the highest order, the second derivative, is positive definite. This equation we wrote down here, Laplace's equation, is an example of an elliptic PDE. Turns out that this thing is positive definite. Which actually makes sense, right? Because what is A in this case? Well, think about it. So remember the Laplacian is like fxx, the second derivative in the x direction, plus the second derivative in the y direction, plus the second derivative in the z direction. Yeah, that's the Laplacian of a function. So what is A in this case? It's the identity, right? Because it's just picking out those diagonal terms, the one that has second derivative in the same variable twice. Yeah? And the identity matrix is pretty clearly positive definite. Yeah? All right. So the theory of elliptic PDE is gorgeous and so nice. You should go pick up, what is that book? I forget. One of those big scary yellow math books that I'm sure none of you will actually pick up goes through this theory in lots of detail. And you can prove all kinds of things about elliptic PDE. For one thing, they have solutions, and the solutions are unique, which is nice. But more surprisingly, elliptic PDE are actually regular. There's a very famous theorem from the theory of mathematics called elliptic regularity, which says that any elliptic equation not only admits a solution, but that solution is automatically infinitely differentiable. This is surprising, right? Because if you look at our PDE here, for example, this PDE only takes 2 derivatives, right? So there's no reason why the third derivative of f even needs to exist, right? It could be discontinuous. But in fact, the theory of elliptic PDE and elliptic regularity says that cannot happen. That automatically you can take as many derivatives as you want, and they're all well behaved. So why do we like elliptic PDE? Well, remember, once again, our proof of Laplace's equation here, right? We wrote down this energy and so on and so forth, got there. Yeah? In fact, remember why we did this was to interpolate a function to the interior of that domain omega? We know that our interpolation is smooth, infinitely differentiable. That is a great property to have. Right? And there's also all kinds of nice theorems you can prove, like the maximum principle, right? It says that this function can't accidentally have like a local maximum in the interior of omega, which is good because it shouldn't if you interpolate. Alright, so again, the model equation is the Laplace equation, right? It's exactly the one we wrote down where you just sum up the second derivatives. We put 0 on the right hand side, but more generally you could put down some other given function g, no big deal, and give it different boundary conditions. Right? We gave Dirichlet boundary conditions to our example. Right? We fixed the values around the outside. We interpolated the inside. Yeah? So let's do a quick 1D example. By the way, one-dimensional PDEs are really ODEs, but we can think about them a little differently. So what would be the Laplace's equation in one variable? Well, it would be f prime prime of x equals 0. Yeah? So obviously if the second derivative of the function equals 0, then in general f of x equals ax plus b. Last I checked. World's easiest PDE to solve. And right, so this is a little bit of a pedantic example, but it does show you what can happen with different boundary conditions. So for example, let's say that I have Dirichlet boundary conditions. Yeah? Well, then that means that I've specified, I have 2 points A and B, and I specify f of A and f of B. So what do you think the solution is? The Dirichlet boundary condition, well, it's just a line through those 2 points. Yeah? Now what would Neumann be? Well, remember that Neumann boundary conditions specify the derivative of a function on the boundary. Yeah? But what happens, so here's A and here's B. What happens if my derivative goes this way here and that way over there? Is there any line that looks like that? No. This example is what we call a compatibility condition. So in general, this is your first example of a PDE with boundary conditions that looks totally reasonable, but has no solution, right? If I solve f prime prime equals 0 and I set the derivative on the 2 endpoints, the derivative better be the same on both sides. Yeah? These things get even more subtle in higher dimensions. And, yes, Catherine.
What's the reason why, you couldn't have your function, match?
Because I proved to you that the function has to be ax plus b. And that's a line. Yeah. And if your conditions are compatible, then if you take that line and you shift it up and down, it's still a valid solution, right? So you either have a non-unique solution or one that doesn't exist. That sort of looks like an overdetermined system of equations, yeah? Or underdetermined. See how these stories all fit together? PDE is really just secretly linear algebra. Okay. A parabolic PDE is one where you have a semi-definite matrix, which means all of your eigenvalues are either positive or 0. Yeah? At least when it's symmetric. By the way, you can always make asymmetric, right? Because partial derivatives commute. Anyway. Now, our story gets slightly less, just like in the case of conjugate gradient.